Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, how do you monitor the robots? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we're returning to the industrial side of robotics to find out more about how robots are used for inspection and maintenance, and also how we can monitor the robots themselves to improve precision and quality. Before that, I'd like to remind you about our competition to win your very own Robot Talk t-shirt. Our winner for February was Frank Forster, and we'll be selecting another lucky winner at the end of March. For more information about the competition and how to enter, check out robottalk.org. And don't forget that you can send in your questions for my future guests, either by contacting us on social media, we're at Robot Talk Pod on all the socials, or you can submit questions via our website by going to robottalk.org. So, with all that said, let's get on with this week's interview. I recently had a great conversation with Andrew Starr from Cranfield University, all about robot maintenance and railway inspection robots. Today I'm talking to Andrew Starr, a professor of maintenance systems at Cranfield University, whose work focuses on monitoring of mechanical systems. Hi Andrew, great to have you on the podcast.
Hello Claire, and thank you for inviting me.
You're working on robotics for industrial maintenance. So to get us started, can you give a bit of an overview of some of the different ways that robotics is being applied in this area?
Yeah, robotics has been used in the manufacturing industry for decades now. And what's been interesting over the last 10 years or so is the move into more mobile robotics and mobile manipulators, that is, vehicles which are a combination of some kind of unmanned ground vehicle with a robot on top. And it's of great interest to those who have high-risk environments for people to do really detailed tasks. So some examples of those are nuclear industry, railway, some aspects of aerospace, and really the applications are ramping up very rapidly at the moment.
So this is I can never remember the 3Ds. Was it dangerous, difficult, dangerous, and dirty tasks?
Certainly, with the partners that we work with, those are some of the things that come up. And often the people who are asked to do these kind of tasks are also there at night. Consider, for example, in something like inspection of a railway tunnel. It's a horrible place to be. It's dark and it's dripping with water, and it's got to be at a time when the trains don't run. So people are doing that during the night, and it really is a risky, dangerous place to be because it's slippy. The trains aren't there to run you over, but it's a pretty rotten job. So if we're able to move those jobs into closely supervised situations where people are remote, either in a truck or a porter cabin, or even better, in a comfortable office, and even better than that, if there's more autonomy in the task, then the tasks can be supervised during the day, or even for part-time workers, as opposed to people who are there on the spot.
Yeah, absolutely. And although your work now uses robots to monitor different mechanical systems, you actually began your career working on monitoring the robots themselves, specifically robots on car assembly lines. So what challenges in this area have now been solved, and which ones remain?
Yeah, I was privileged to start my research career with a group at Manchester University who were a spin-out company, and sadly no longer in existence, but the company that I worked with for my PhD was Ford. And I worked on 4 different sites, 2 in Germany, 2 in the UK. And there were lots of robots in use doing things like welding, component handling, and application of some specialist materials like sealants around windscreens, for example. One of the problems basically a robot is supposed to get something from A to B. It's just a manipulator. And one of the problems that turned up was that they didn't get from A to B at all, or alternatively, when they got to B, they were quite inaccurate. And that's really difficult to measure. It's not just at arm's reach. You're dealing with a machine that is quite quick and heavy and often handling tools which you wouldn't put in the hands of a human operator because they're too big and heavy, and they've got no guards on because they don't need it. So the machines are in cages. So the result, for example, of an imprecise weld is that either the welding gun isn't on the edge of, say, a car body around a doorway or a windscreen, misses it completely, or it's on the edge, in which case it leaves a raggy edge, or it might strike the high quality bit of the car body that would be visible afterwards. So some of those could be covered up with a rubber seal or something, so they might pass, but quite a lot would fail. Yeah. And the errors of end positioning were at least 10 millimeters in some cases.
Wow.
So that's really difficult to pick up optically. So it was being picked up by quality control. So the spin-out company at Manchester, Wolfson Maintenance, had been involved in dealing with some of the welding transformers at first, and they were getting too hot. And they were using a technology that had only just come out of the military, which was infrared imaging. It really cost an arm and a leg at that point, and it was all displayed in monochrome, but it could detect blocked welding transformers which had got dirt in them, and it could detect the over temperature in these. So having seen that, I extended this idea to using video to measure the position and to detect the repeatability, even with the limited number of pixels that we had on video cameras at the time. I wouldn't say it was very portable, but with a tripod, you could get the camera static, and with a trolley load of gears, batteries, desktop computers, 50-meter extension cables, you needed all of that to get on the production line. But then you could actually detect the movement of the robot itself in practice. So those were some of the early tests. But later on, I met probably about 10 years ago a company in the Midlands who refurbishes industrial robots, and asked them about some of the faults that had led to this imprecision, which basically was either poor tuning in the control circuitry or damage to some of the closed loop sensing, or mechanical forward loop components, which would have things like backlash in gears and shafts and bearings, and damage to motors and so on. And essentially they told me, all of that's been fixed. However, they still had things that they needed to replace before robots could be returned into the second-hand market. They weren't just resprayed yellow or orange or green, depending on the manufacturer. One of the problems that they still encounter is multi-core cables. So we need to get quite high currents to the end of some end effectors like welders.
Okay.
And they bend continuously backwards, forwards. And as a consequence, those turn into the same phenomenon as you get using a piece of wire wool. So imagine you've got a neat new wire wool scourer or something, and after a few uses, it's now a kind of prickly pad which goes through your rubber gloves and scratches everything, and it's at end of life. Well, copper braided cable does this, and it even punctures its own insulators.
Yeah, that's not good.
So these are the real life things about machines that, as they come fresh out of their box or their crate, appear to be perfect, brand new. We can't think of them degrading. But my job, my whole career has been about predicting when and how will this degrade, and how can we detect it, or even better, prevent it, so that it doesn't break down in ways that are either dangerous or produce loss of production or destroy things around them and cause expensive repairs.
Yeah, so I've heard about this concept of predictive maintenance. Would robots these days I guess they'd have a lot of sensors or whatever built into them to try and detect this rather than just waiting for a regular scheduled inspection or whatever?
Yes, to a degree. So if it's possible to work out that a component degrades in a pretty regular manner, then what we do is redesign it and make sure it doesn't do that. If you can't redesign it, then you build in something that detects it. And for a long time now, those approaches have been called a canary after detecting carbon monoxide in a mine. And those could be quite simple, things like going over temperature, for example. Everybody's got these in things like central heating. And others are more complex, because in robotics, you're often looking for acceleration up to a speed, some kind of continuous speed or path, and then deceleration down to zero, and we want some kind of static point. And that's quite hard to achieve perfectly. So as a consequence, we have to deal with things like overshoot of electromagnetic and components with mass, that they all don't quite behave as you want them to. They don't accelerate properly, and then they don't stop properly. And then in particular, things like a continuous path is really hard to achieve. And the more complex it is, the more motors and axes are accelerating and decelerating to maintain something that we think is quite a simple kind of task to program. So detecting all those, some of those are monitored, but essentially they're a closed loop system. And I detected some of this problem early on in some of our automotive work, when the fitters, who were highly skilled technicians at repairing and controlling and managing the robots, said, oh yes, one of the problems with our gearboxes, and they were backlash-free designs, really clever design, but the robot doesn't know where the gearbox is. And the fitters had discovered that if you gave the robot a hearty shove, you could get it to go round one notch on its gear, and the robot didn't know, because it's just a dumb machine. And depending on where the rotary encoder is to pick up that axis, typically they are very close to the motors on robots, because it's easy to assemble them there. But that means that the end point is really at the end of all the slop in the gearboxes and the shafts and the bearings, and the programmers have to just assume that it's in the right place, which it rarely is. So all of those things are kind of expected, but there's things that happen which are not expected as well. And you've seen some control systems in the aerospace industry recently doing some things that we really didn't expect them to do, with some really serious outcomes. And hence being able to catch the unexpected is something that's really important, where safety is concerned, and productivity and damage to the capital equipment.
Yeah, the unknown unknowns are always the challenging part.
Very much so, yes. And the uncertainties and the unknowns are a real big issue. And something that I do regularly with our researchers, particularly new PhD students, is to think over how we handle that. And there's a huge enthusiasm for data-based solutions to this these days. That the artificial intelligence or the deep learning will find everything. And I always challenge them to think about, well, okay, but can you pick up something like corrosion or delamination of some surfaces. Metallic surfaces are really important for keeping things rotating or sliding. And when they get damaged, they don't progress in a nice, smooth manner. They splinter off. They create spalls on a surface. Or material floating around in lubricants appears as bits, and we count them. And if there's something that parts company with its surface and ends up in a lubricant, then it doesn't arrive in ones and twos. It arrives in thousands, and it arrives in lumps and clots. So actually, data-oriented solutions aren't that great at predicting this. But the reason I can predict that it might happen is that there's an awful lot that we know about this. There's some physics, there's some experience. We've got good analytical models of the way these things behave. So one of my big ambitions at the moment is to try and get a kind of unification of models which are physics-based, experience-based. We had expert systems back in the 80s and 90s. Nobody talks about them anymore, but some of them were really clever because they captured that expertise. And today we can run the whole lot in parallel. So if I get some kind of probability out of a data-oriented solution, and then the expertise said, oh yeah, okay, we've seen this before in this kind of pattern, or we've never seen this before, so it needs investigating further with more data, more frequently, and perhaps call in people, then we can get much more robust systems. And that, I think, is quite important rather than nailing our colours simply to one mast.
Yeah, definitely. I mean, I think there's something sort of tempting and pleasing about the idea of being able to just automate everything and have it just, do its own thing and leave it alone. But you can never really replace the expertise of humans.
Yes, and increasingly we've worked in regulated environments, and regulations have a distinct purpose. So, we've heard about more regulation in food, in pharmaceuticals, lots of things in daily life. And I've done quite a lot of work with the transport industry, and it's not surprising that things in aviation and railway transport really have important rules in place. And it would be very foolish to try and train systems from scratch without embedding those rules.
Yeah.
And there are things about speed and force and checking and double checking, and trying to deal with the human factors and the known degradations that we have with materials, components, and systems.
That leads quite nicely into the next topic I wanted to talk about, which was an autonomous railway inspection and repair robot you've been working on in collaboration with Network Rail. So when I think about this kind of task, I think, it seems like it brings together a lot of different challenges, from computer vision all the way to like dealing with weather. So can you tell me about this robot and some of its features?
Yeah, we're on our third generation of railway robots now, and although we have built some for some specific tasks, there are others in the industry which are dealing with some specific areas of repair and job control. We started about 5 years ago with a demonstration as part of the European Shift to Rail programme, which, despite that political manoeuvre that we remember, we were still in Shift to Rail, and Network Rail in particular was committed to a number of projects within this really big €1 billion programme. And part of the area that we got involved with was about command and control systems.
Okay.
The company had committed to a physical demonstration of jobs coming from a computer system, which then needed to be transmitted to an autonomous vehicle, which would then go and do its job and then report back what it had done, and to report that the job was finished or needed further action, and to go back to the initiating command system to deal with that. So getting from a command system, a fairly conventional idea of an industrial job control system, all the way down to physical demonstration requires some transmission of messages and deciding what's in those messages, but when they're received, starting the vehicle in some kind of search pattern to go and find its location and what the incident is that needs dealing with, then some kind of action, and finally those steps in reverse once it knows it's done it. So in the first robot, we looked for simulated faults, which basically were a red feature, and the whole thing was done at scale. We didn't do it at a tiny scale, we did it at a medium kind of scale, at about 1/10 scale vehicle, which is approximately 5-inch gauge. And that means you can buy the track, you can buy some components to run on it, and we automated the vehicle with an Arduino, but it also had a robot on board, and the robot and the Arduino continuously argued about who was in charge. But it did the job, and it went around several exhibitions showing the demonstration that it could find the target, and if it was on the left rail, then it instructed the robot to do its job on the red target on the left rail. And then if it was on the alternative rail, then it could demonstrate that it had multiple responses to its inputs. Worked very well, except when we had to do a demonstration on a red carpet. And then, of course, it picked up inputs everywhere. Yeah. These are the kind of practical concerns that one has to deal with.
Yeah.
Later on, and just as we hit 2020 and the pandemic, we took delivery of a ClearPath Robotics Warthog, which is one of their larger autonomous ground vehicles. And this could do a lot more for us because it carries a package of instrumentation for navigation and for more precise localization and situational awareness. So, for example, GPS for location and navigation, but LiDAR and some additional sensing that we put on to detect things close up. And you mentioned cameras, multiple cameras for detecting different parts of the view. And one of them we fitted on the end of a robot arm as well, on top of the vehicle, so that it could position the camera in different places. But of course, at the beginning of the pandemic, everybody had to go home and we had hardly anybody in the laboratory. What I think I might have done in retrospect is to change the wheels on the vehicle to railway wheels. But at the time, we wanted to make sure that this rather expensive vehicle that didn't belong to us was completely, that any changes could be completely undone. So we designed and built a trolley for the UGV to run on, and it used, well, continues to use rollers which transmit the power from the tires of the unmanned ground vehicle, the Warthog, to the track through railway wheels, through some belt drives. So that's a little bit clunky. However, it enabled the thing to propel itself up and down the railway. We had to learn how to get the vehicle on and off its trolley. The trolley we can manage with about 4 people quite easily, but the Warthog weighs about 200 kilograms. So you don't lift it, you drive it. It's very agile, but we had to get it up ramps onto the trolley. But once we'd done that, we were able to do a series of increasingly complex tests. We put a piece of railway track on a corner of the runway at Cranfield. Cranfield has its own airport, so there's a fair amount of space, which is a real asset compared to a city centre university.
Yeah.
So we were able to use this piece of track without having to ask anybody. And if you want to go and close a railway, that is quite an important sequence of events to do. So it's possible to do it for maintenance and for changing track. But having your own piece of track makes a big difference to getting things ready and testing out all the subsystems. And we needed to test things because, for example, GPS is fine outdoors with plenty of sky, but there's about 10% of the railway where it doesn't work. The reason for that is things like buildings and tunnels and cables. The tiny signals that you're looking for from the satellites are easily disrupted by electromagnetics. So Faraday cages are no good. Canyons between buildings and cuttings on the railway, they're no good. So we really had to have additional packages of instrumentation like encoders, inertial measurement unit, and others, all of which were coming together in a data fusion algorithm to estimate positions between GPS fixes. The GPS guys also will happily sell you real-time kinematics, RTK, which gets your precision down to 20 millimeters. But on linear assets like railways or highways or pipelines or electrical distribution, you'd have to have a repeater every 200 meters. So it's an absolute non-starter. You need something that's more universal.
Right.
Having tested some of these subsystems on our own site, we then did a number of demonstrations at heritage railways. Heritage railways are real regulated railways, but they're much easier to close down than the main line. And as a consequence, we were able to have a whole railway at our disposal. And we've been to two different places, the Northampton and Lamport Railway, which is quite close to us, and the Ecclesbourne Valley Railway up near Derby. And both of these offered us excellent facilities. And in brief, when you're trying to do these kind of outside activities, you need to get people there, you need to park them up, you need to feed them. And of course, you need a railway, but there's plenty of railway about. But having all the other stuff nearby and having good welfare for the team is important. I think you also hinted at the range of skills that we needed to be able to do this. So part of my role is to bring together a team of people who can deal with the whole range of tasks that we need for building some of the robotics from scratch, modifying things, modifying commercial systems, and that involves the mechanics, the electrics, the computing, the instrumentation. And then there's some systems where, frankly, we don't know what we're going to get until we get it. And hence I need really quick thinkers who are willing to get their hands dirty. And fortunately, at Cranfield University, I have those in abundance because we're able to work in not just our permanent postdoc team, but also some very keen PhD students and master students. I don't have any undergraduates at Cranfield, but if I did, they would be involved too. And we've done some great team efforts.
Fantastic. I mean, it sounds like a really interesting and fun project to work on, especially the inclusion of the opportunity to work with model railways, which is always fun.
Absolutely. Well, we started at a relatively small scale, not least of which we did a number of exhibitions in the UK and around Europe. And having things at scale means that it could be packed in a big kind of flight case and shipped out. I mean, it's a van load rather than rather than a suitcase full. But you can show a lot of activity and a lot of proof of concept at scale. But then the railway partners wanted things showing in real life. So having built the UGV version, we then went on to convert a more proprietary rail trolley. Now, many of them have petrol or diesel engines, but there's a new version from a company in the UK that has electric propulsion. But it really is a dumb track trolley. Its main control, other than peeping its horn, its main control drives it away from you.
Right.
And you can load it up with up to a ton of materials and tools, And if you want it to drive in the other direction, it'll literally unscrew the hand control, put it in the other end of the vehicle, and then it'll drive back, always driving away from you. So without any technical drawings, because we were not allowed access to them, we needed to get into the circuitry that dealt with the propulsion and the braking, the warning lights and the warning sounders, and we put in interfaces to control all of those with suitable controllers and amplifiers. And then the top layer of computing is a very sophisticated, high-powered bit of portable computing with lots of different inputs and outputs. And then we retrofitted all the instrumentation that we'd had specified on the Warthog and put that in from scratch into the proprietary track trolley. So that takes the form essentially of a 4-foot square base, and any payload can be applied to that. And back in May last year, we demonstrated an ultrasonics payload from a well-known railway manufacturer, mature technology, but it needed to be tested in this robot control environment. So we did that at Wirksworth on the Ecclesbourne Valley Railway. And you mentioned things like waterproofing earlier. You've never seen so much rain in 2 days. It absolutely tipped down. And in the gaps between the rain, well, we did operate during the rain. Everything was waterproof.
It's got to be in this country.
Well, yeah, hot and cold and waterproofing, vibration and dust. These are normal things that the operational equipment has to deal with. And after we've finished doing proof of concept, then the next stage is to think about how do we get this into the supply chain. And that needs a good specification. And so proof of specification is a lot of the job that we're doing. But yes, getting everybody up there in their protective equipment. Everybody knows what PPE is these days, but in that case, it was orange gear, plenty of warm layers and gloves, hard hats. And in terms of welfare on some of these sites, we need to get gazebos for shelter for some of the equipment, but mainly for people. Plenty of flasks of hot water for tea and coffee, and batches of sandwiches in, because you've got to get real people to do these real jobs and to look after them while we're out on site.
So much more to it than just pure robotics.
Well, to some extent, by that point, the robot is the easy bit.
Andrew, it's been great chatting to you today. I've been speaking to Andrew Starr, a professor of maintenance systems at Cranfield University. Thank you.
Thanks, Claire.
Thanks for listening. If you enjoy Robot Talk, please do share the podcast, subscribe, and leave a review to let us know what you think. And make sure you check out our social media channels to see a photo of the latest version of the railway inspection and repair robot that Andrew is working on. We're at Robot Talk Pod on all the socials. Next week, I'll be talking to Patricia Shaw from Aberystwyth University, all about home assistance robots and robot learning and development. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.